Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to talk about spherical geometry. Spherical geometry is very important for questions having to do with navigation on the surface here of our favorite sphere. So let's say I decide I want to go and take a trip to Seoul, South Korea. Unfortunately, there are no direct flights from Memphis, but instead there are direct flights from Atlanta. So I'm imagining I'm going to start here in Atlanta, and I'm going to fly to Seoul in South Korea. So Seoul is about there. Okay, so that's the path I want to do. So let's look up flights. So I'm going to go pull up a website here that has flight paths on it. So here's the question. Why is my flight going above Alaska like that? Why doesn't it fly directly due west? Right? Seoul is a hint north of Atlanta, but it's about the same latitude maybe as Baltimore. So why are we flying up all the way to this really far north point above Alaska? Okay, so I encourage you to pause the video for a moment here to see if you can come up with some ideas for why that might be the case. Perhaps surprisingly, the reason for this is that the airline has found the shortest path, and the shortest path means the one that uses the least amount of jet fuel. Okay, so let's try to understand that statement. So let's start with this piece of string. If I leave my string loose like this, it takes whatever shape it feels like. But if I pull it taut, it's going to follow a straight line between my two hands here because it wants to take the path that is the shortest. Okay, we're going to use the string as a tool on the surface of the Earth. So what I'm going to do is I'm going to put one end of my string on Seoul, and I have some ridiculous zigzaggy path, but I'm going to pull it as tight as I can and make it go through Atlanta. Let's see, where's Atlanta? There's Atlanta. Okay, it's kind of on, I actually made it on the bottom of South Korea, but that's close enough. And we see, right, my string that I pulled taut is now following pretty much the flight path. It's not exactly right because my beach ball is a little bit squishy, and ideally for this experiment I'd have three hands, but that's not so bad, right? That's the flight path here. Okay, so let's take a look at this on the computer where we can see this a little bit more precisely. Okay, so here we see basically the flight path from Atlanta to Seoul as we saw it on the globe with the string. And now I can switch it on the map, and now we can see the same path, but now it's represented on the map instead of being on the globe. Okay, so let's switch back again to the globe view, and that explains the flight path that we saw. Okay, so on the homework assignment, you'll take a look at a couple more of these things. Now this interaction between the globe and the map is maybe a little bit weird. So there's a beautiful video by Professor Hannah Fry of Cambridge University that I have linked down below in the description box, and I've also linked it from Blackboard. Take a look at that if you want to learn a little bit more about map projections. We're not really going to talk about map projections so much. We're going to instead focus on what are these shortest paths on the sphere called, and how do we describe them geometrically. Okay, so here's a little GeoGebra applet that I found. This shows us the shortest path, but it shows us also what happens on the globe if we follow the straight line path from the map. And the map is called the Mercator projection, is the name of that specific map. And the Mercator projection is the one that, for instance, Google Maps also uses. So it's a very, very commonly used map projection. Okay, and this one conveniently allows us to see both the path that's flying along the shortest path, but it also shows us what happens if we fly due west. It's a significantly longer way that way. Okay, so now let's try to understand what these paths on the globe are. These paths, shortest paths in general, are often called geodesics or geodesic arcs. So I think it's easiest if we think about this first on my transparent sphere. So I'm going to start by introducing a notion called a great circle. So what I want to imagine is I want to imagine taking a circle that I'm going to draw on my globe that cuts it into two halves that have the same size. Right, so I want to imagine taking, I don't know, some kind of a bread knife and slicing through my globe. So an obvious way of doing that is to just follow the equator. And so I'm going to follow the equator, kind of an imaginary equator, because this is, I'm sort of freehand drawing this. Oh. Okay, not the best equator, but also not the worst equator. So that's cuts my sphere into two equal hemispheres, the northern hemisphere and the southern hemisphere. It's maybe more obvious if I look at the actual globe, right? We see the equator here and this dark blue line here that's cutting into the northern hemisphere and the southern hemisphere. Okay, but there are other ways of doing this, right? I can cut it like this, going from the North Pole to the South Pole, and then on the opposite side, 180 degrees away, I also go from the North Pole to the South Pole. And conveniently on this beach ball, that's the seams where the plastic got attached together, so it's very easy to do it, right? And that cuts my sphere into two equal halves. So for on the Earth, these are lines of constant longitude, and these are called meridians. So what we're doing is we're taking a meridian, and we're taking the meridian 180 degrees away from it, and those two things together slice my globe in half. Okay, we don't have to do it in this sort of nice orderly way. We can also do something that's oblique. So this is going to be harder for me to draw, but we could imagine something like, let's draw this guy right here. And so this in red, I don't know if you can see that so well, this also slices my globe into two halves. Okay, so now what we do is we're going to define these circles. We're going to call them great circles. And the construction we're going to have to find the shortest path between 2 points is if you give me a point here, A, and let's say a point B. What I want to do is I want to find the great circle that passes through A and B. So let me be lazy here and put A and B on one of these great circles I've already drawn. So let's say A here and B here, right? This is on my red great circle. Then this red great circle has two arcs. There's this short arc here between them, and that's going to be the shortest path between my 2 points. And then there's the long way around, which is less interesting to us. Right, so this is called a geodesic arc, or an arc of great circle. So a natural question is, how do I find these things? Right, this is, I sort of eyeballed this. How do you really find that? Well, that's a very nice geometric construction. So here what I do is I take my 2 points A and B, and I take the center of my sphere. And now I imagine a plane that passes through A, B, and the center of the sphere, and that plane is going to slice my sphere precisely in this red great circle that I drew by eyeballing it. So let's take a look at this on GeoGebra so we have a more precise way of constructing it. This is getting to be a little bit messy and imprecise. Okay, so here is GeoGebra, and so this is GeoGebra through the web interface. As you can see, the URL is geogebra.org/3D. If you're doing this on the iPad or whatever, you're looking for the 3D calculator. Okay, so I'm going to go to Tools here, and you see here is our three-dimensional coordinate plane. I have my X, Y, and Z axes here, and I can go ahead and make my XY plane have a grid on it if I like. I'm going to go ahead and do that. And I'm going to take actually I need to define a point first. So I'm going to define a point here, and I'm going to change its name to O, because it's going to be the center of my sphere in the next step. So now I'm going to take a sphere with a center at O and a given radius. I'm going to give it radius, let's say radius 5 for fun. Okay, and oops. I now have my move tool on, and see I can move my picture around. Now I'm going to go ahead and I'm going to put 2 points on the sphere. Let me just go ahead and close that. And so now I have 2 points on the sphere. I'm going to come back to my move tool, right? And we see here I have my 2 points on the sphere, A and B. And I choose the tool here that does plane through 3 points. And I go boom, boom, and then my third point is the center of the sphere. Come back to my move tool, right? So this is what it looks like. I have a plane that slices through the center of the sphere and also goes through the 2 points on the surface of the sphere that I was talking about. And now let's go ahead and intersect two surfaces. So I'm click here on my plane, and I click over here on my sphere, and that intersects the two surfaces. I'm going to grab my move tool and show how in this slightly darker blue here, we now have the great circle that goes through A and B. Right, so I can move A and B around, something like that. Right, so that's kind of like the configuration of, let's say, Atlanta at B and Seoul at A. Right, it was roughly something like that. Okay, so that's how you construct a great circle, where we did all the steps of the construction carefully using GeoGebra. Okay, so the key theorem from spherical geometry is that this short arc of great circle that we constructed is actually the shortest path between those points A and B if we are forced to stay in the surface of the sphere. And that's what allows us then to understand that flight path that we saw at the beginning of this video. So I've given some links to other videos, notably the one by Professor Fry that's down below. Be sure to check that out. I think it's a really fun video. And I also have links to the two websites I use, the flight path one and the geodesic circle one. And I also have a link to the GeoGebra worksheet online that I used for the picture up above. Go out there, play with all of them, see what you like, what you don't like. Take a look at the homework problems that have to do with spherical geometry, and see you on the next one. Happy mathing. Hope you enjoy. Thank you.